Hello class. These notes are going to be over one-dimensional motion in the x direction. First, I'm going to touch on the metric system. We seem pretty weak in that area, and significant figures. Those are going to be important on the AP test. So the first thing I'm going to cover is the metric system. We're going to need to memorize what I write down, so you might want to make note cards out of this. We have 3 dimensions in the metric system. Mass, which is measured in grams, which we use a little g for symbolizing grams. Length, which the base unit is the meter. We call it the SI unit. Stands for Système International in France. We call it the Universal International System of Units. We symbolize meter with an M. And then there's volume. The SI unit for volume is the liter. We symbolize it with a capital L. We also use symbols as far as the 3 dimensions are concerned. M for mass, L, a cursive L for length, and a V for volume. Those will become used for other things as well later on in these notes. There are several prefixes that we can add to these base units right here that tell us that there are more or less of them. So let's just cover those here. I'm going to make a table for the prefix, the abbreviation, the power of 10. The metric system is all based on the power of 10, and the conversion factor. The first prefix you're going to need to know is the mega. Then we have the kilo, the centi, the milli, the micro, and the nano. These are definitely ones that you're going to need to know off the top of your head and memorize. The abbreviation for the mega is the M, kilo K, centi small c, milli small m, micro looks like a U with 2 tails, and nano is a little n. The powers of 10 associated with these, with the mega, it's 10 to the 6th, kilo, 10 to the 3rd, centi, 10 to the minus 2nd, milli, 10 to the minus 3rd, micro, 10 to the minus 6th, and nano, 10 to the minus 9th. And the conversion factors that we will use with these is a million for the mega, 6 zeros, 1,000 for the kilo, 3 zeros. We'll use 100 for centi, 1,000 for milli, a million for micro, and a billion with 9 zeros for nano. Now the difference in these is that the kilo is big, the milli is small. So there are more grams in a kilogram where there are more milligrams in a gram. You're going to need to know how to convert units. I will just do a quick conversion here. Let's say that we have 1,018 meters. And we need to convert that to kilometers. So the first thing we do is we write the quantity given. We assume it to be over a 1. We draw an arrow to drag down our units diagonally. So now we know our conversion factor with the meters goes in this spot right here. There are 1,000 meters in a kilometer. Looking up here. So the 1,000 is going to go down here. 1 kilometer goes up top. We cancel out our units. We do have a kilometer here. We multiply the top with parentheses, and we divide by the bottom with parentheses, and that gives us 1.018 kilometers. If you don't have the parentheses here, and you have more numbers than just the ones here, let's say we're doing multiple conversions, then whatever number is right here is going to be divided by whatever number is right here, and then it's going to multiply by everything else, and you may end up with the wrong answer. So it's always good to have parentheses on the top, parentheses on the bottom. That way you're sure to get the right answer. Let's say that for a multiple conversion, I am going 80 kilometers per hour, and I need to convert that to meters per second. So I would write the quantity given, 1 hour. I would draw an arrow to drag my units down here. I know that there is 1,000 meters in 1 kilometer. So I would write my conversion factor, cancel my unit. I now have my meters, which is what I need, but I still need to convert my hours to seconds. So I draw an arrow to drag my units diagonal. My hours are going to go on top. There are 3,600 seconds in 1 hour. You need to know that conversion. You will be making it a lot. I cancel my units. I now have the seconds I'm looking for. I can multiply my top with parentheses and divide by my bottom with parentheses. Probably don't need to include the ones in something like this, but it's always a good thing to get into the habit of just writing out your multiplication problem and division problem. And so whenever we do that problem, we have 80,000 divided by 3,600, 22.22 meters per second. The next thing I need to touch on, and you can pause this video at any point to get the notes that you need whenever I go on. The next thing I need to cover is significant figures. Significant figures. Significant figures are going to be important on the AP test. You will be allowed to give one significant figure over or one significant figure under the amount that you need, the amount of significant figures you need. If you give more than that or less than that, then they will count that against you. So, let's talk about significant figures. Most of the time you're going to be multiplying and dividing. There are some rules that I know that you guys have studied. Basically, you've studied both addition and subtraction rules and multiplication and division rules. Like I said, most of the time you're going to be multiplying and dividing. So I'm just going to cover some of those. And I'm just going to give examples because I know that you guys have learned these. You have supposedly 10.35 times 9.4. Whenever you're giving the answer in significant figures, you always want to use the measurement with the least amount of significant figures. There's 4 here. There's 2 here. So your answer will need to be in 2 significant figures. So your answer will be a 97. Let's look at 0.00947 divided by 0.000135. Zeros preceding a number do not count as significant. There has to be a decimal with zeros after the decimal for the zeros to count. Any zeros before a number do not count. So in this case, you only have 3 significant figures here, 3 significant figures here. They are equal. Your answer will need to be in 3 significant figures. So your answer is 70.1. You need to be doing these in the calculator and see where I'm rounding this. And rounding is important. You need to make sure and round. $200 with a decimal divided by 19.32. This one only has 3 sig figs, whereas this one has 4. Looky here, there's zeros that have a decimal. So these zeros do count. It is after a number, and there is a decimal present. We will only use 3 significant figures in our answer, so your answer will be 10.4. However, when we're working with whole numbers, let's just say we were given the whole number of 200. 200 pennies, for example, that's a whole number, divided by 1932. Let's just say that's the amount of money we have. We're trying to get a percentage, something like that. We will not count this number as having 3 significant figures or as having 1 significant figure. We will just not count it if it's a whole number or given as a whole number. So we will only count this number right here, which has 4 significant figures. So your answer is going to be 10.35. Now, if this were not a whole number and it was given as a measurement, then the answer would only have 1 significant figure, and you would have to round that down to 10. If you rounded that down to 10, and you did not put a decimal there, that would be 1 significant figure. Alright, I am done with sig figs. Let's move on to one-dimensional motion. In the x direction. We've got to define a few words first. I've already covered distance and displacement with you guys. It's important to cover again, especially whenever we're talking about one-dimensional motion. Distance is the amount traveled. Displacement is measured from point A, or from your beginning point, to point B in a straight line. So for instance, if You start out in the science hall, you end up in the junior hall, but you take a roundabout way to get there. You go through the 200 hall, then through the 300 hall, and then through the 400 hall so that you can pick up something from a teacher, and then back around to the junior hall. Your amount traveled is quite large. Your distance traveled is large, whereas your displacement is only measured from the science hall to the junior hall. Point A to point B. We need to talk about speed and velocity. Speed is the distance over time. It shows magnitude. Magnitude is just a measurement, just a number. We'll say amount. Whereas velocity is measured in displacement over time. It shows magnitude and direction. Which gets us into the words scalar and vector. A scalar is magnitude. A vector is magnitude plus direction. So speed is a scalar. Velocity is a vector. We graph velocity. We don't graph speed. And then we need to talk about acceleration. Acceleration is the change in velocity over the change in time because it is a change in velocity and velocity is a vector, then that means that acceleration is going to be a vector. Velocity is a vector and speed is a scalar. I talked about kinematics in the last notes. We will be doing kinematics. Kinematics is the study of motion in terms of an object's displacement, velocity, and acceleration. In order to study the motion, or to use kinematics, we will need several formulas to calculate its displacement, velocity, and acceleration, and the time it takes to get from one place to another. And these formulas I will refer to as the Big Five. And you will need to memorize these as well as the metric system The first one is change of x equals your average velocity times your time. Your second one is v equals v naught plus at. This will be your final velocity. This is your initial velocity. Basically, this says your velocity at 0 or origin plus acceleration times time. Your third one is x equals x naught plus v naught t plus 1/2 at squared. X is position, your change in position, your final position, your initial velocity, time, acceleration, time squared. 4, x equals x naught plus vt minus 1/2 at squared. So here we're using final velocity instead of initial velocity. And 5, v squared equals v naught squared plus 2a x minus x naught. Big 5. Put these on note cards. Write them over and over and over until you know them. We will be taking all or nothing quizzes over things that you need to memorize. I'm going to show you how to use these formulas in an example. We have a car that is initially traveling 10 meters per second. Then accelerates. Oop, going off the screen, sorry. For 4 seconds at a rate of 2 meters per second squared in a straight line. How far does it travel? The first thing I like to do when I'm working problems is to circle what I'm given. And underline what I'm looking for. Right there. The second thing I like to do is I like to list all of my variables here. So all of those variables that are in that big 5. So I have my final x, my initial x, my initial v, my final v, my acceleration, and my time. I think that's all of them. Okay. And then I fill in what I know. I know I'm looking for how far does it travel. So I'm looking for my final x, my final position. That's what I'm looking for. I can assume in this question that I'm starting at 0. My initial velocity says that I was initially traveling 10 meters per second. I accelerate, but I don't know what my final velocity is, so I can't fill that in. It does tell me that I accelerate at a rate of 2 meters per second squared, and it tells me that I do this for 4 seconds. So I have all my variables listed out here. Now what I do is I go and see if I can find one of the big five in which I have all of these and what I'm looking for. So sticking that back up there, I can see that I'm looking for my X, so I need to pick one with an X. Here is one with an X. I do know my X naught, I know my V naught, I know my T, and I know my A, and I know my T. So this formula right here looks like right off the bat it'll work. So I'm going to write that down. So X equals X naught plus V naught T plus 1/2 AT squared. And it's already set up for X, so I don't have to manipulate it. So I'm just going to fill in my numbers. X naught is 0, V naught is 10, times my time, oh, and I need to put my meters per second in here, always use your units, times my 4 seconds. It'll help you decide whether you're getting the right answer or not. 1/2 times 2 meters per second squared, times my time squared, X equals, I can take the 0 out, that's going to be 40 a second, 40 meters, plus the 2's cancel out here, and I square my 4, so that's going to be 16, my second cancel, 16 meters, and then X equals 40 plus 16, 56 meters. There's my answer. My unit says meters because my seconds canceled here, my seconds canceled here, left me with meters and meters. Therefore, I know that my position is measured in meters, and 56 meters should be a good number. So that's an example of how to do a kinematics problem in the X direction, which is all we're working with right now. Y'all have a great weekend, and we'll see you on Monday. Thanks.